Chapter 3 is on exponential and logarithmic functions. We're going to start in the first cluster looking at exponential functions. We'll get to the logarithms in cluster 2. So exponential functions, first of all, in the first section, we're going to focus on specifically the increasing exponential functions. We're going to talk about growth factor of the increasing exponential function and some properties of the graphs of an exponential function defined by y equals b to the x, where b is a number larger than 1. And we're going to look at the graphs of some exponential functions. All right, so in this first situation, reading through, we have this theory that Princess Charlotte's line stretches back 20 generations, which means that she must have more than 1 million grandparents in those 20 generations. So we want to just see if this is possible, true. So we're going to start by making this table, talking about the generation and the number of parents or grandparents. So in one generation back, you've got 2 parents, 2 biological parents. And then 2 generations back, each of those has 2 more, so it's a total of 4 grandparents. And 3 generations back, each of those 4 grandparents has 2 parents. So you have 4 times 2 is 8, or 2 to the third. And so I can continue this with 16, 8, 16, times 2 is 32, 64, and 128. So did we notice a pattern in the output values? Describe how we determine the number of grandparents in a given generation, knowing the previous, so we can multiply it by 2. And then use the pattern we determined to determine the number of grandparents in the 8th generation. Okay, so in the 8th generation, we're going to take 128 times 2, and that'll get us 256 grandparents back in the 8th generation. Now, if we work with exponents instead, we can think about 2 as being 2 to the first power, 4 as being 2 to the second power. They've already demonstrated us that 8 is 2 to the third power, 16 is 2 to the fourth power, 32, that's 2 to the fifth power, 2 to the sixth power, and 2 to the seventh power. So if we're working in terms of the exponent notation, we can see that what stays the same here is it's 2 each time, and the power actually matches up to the input, the generation. So this is going to be a function, an exponential function, where the power is a thing that changes as you go from one generation to the next. All right, so it wanted us to just write this in the column as we've done up there. And then we can write this in function notation. So my number of grandparents or parents, we'll call it P of n, is 2 to the nth power. The base is 2, and the power n corresponds with the number of generations I want to go back. So if I use this equation, I can find the number of grandparents or 20 generations back. It's going to be 2 to the 20th power, and we're going to just evaluate that real quick here on decimals. Okay, so we want to do, I can type in the function, P of n equals 2 to the nth power, and I can evaluate P of 20, or I could just do 2 to the, oops, I hit the wrong key there, 2 to the 20th, and again, we can see that the result here is 1,048,576. So was the claim of 1 million parents or grandparents exaggerated? No, right? Because 20 generations back, there's the possibility for more than 1 million. The P to the 20th is greater than 1 million. Now, that might not be the exact number of parents. Grandparents, sometimes a long time ago, especially in the royal family, there was intermarriage and so on. So there might be exactly 1 million, but it's certainly not exaggerated that we have at least close to 1 million ancestors in our family tree, 20 generations back. All right. So what is the practical domain, number of inputs that make sense for this function? Well, because the input is um, the number of parents, you can't have below 0. 0 would be you, like your individual self. 1 was one generation back, that was your parents. So we can't have 0 as an input. But we can't go below 0, so we can't go into the negatives. So our lower bound on this input is going to be 0, and we'll allow it to be equal to 0 just because that would mean the individual person that we're talking about would be the 0th generation. And then in the case of Princess Charlotte, they only had records that went back 20 generations, so we're not going to be able to go back beyond 20 generations. That's when the records ended. So something like 0 to 20 would be a good domain here. All right, so now they want me to sketch just the first 10 generations. Okay. So what I can see right now, if I'm gonna move the negative side off because we don't really consider negative inputs, and I want to see 10 generations. And so right now I can't even see 5 just because the outputs are too small. So I'm gonna manually rescale this to increase the Y maximum value. I know that in 20 I got up to 1,000,000, so let me try somewhere around 50,000 for, that's 5,000, 50,000 there for our output for around 10. Oh, that was a little too high, it looks like. So let me cut off a 0 right here. See if 5,000 is a little more accurate. Oh, looks like it's about 1,000. Again, I didn't know what it was. Now, I could have just went ahead and discovered it and saw I did only need to go up to 1,000. So my guesses were not extremely accurate, knowing that the 20,000, the 20 generations get us to the million. I was trying to figure out what a good scale would be. Oops, I was trying to get 1,100 here. There. Okay, and I'm going to cut off the 15. I'm just going to manually rescale this to get this to like 11. So it's just bigger than 10. So we can see what this picture looks like. So one of the things we can see about this exponential function is that the growth begins very slowly, and then it picks up and starts growing more and more rapidly. It increases faster and faster as time goes on. So it's only at 1,024 by 10 generations, and by 20, so it's not like doubling or anything, because if it doubled, it'll only be at 2,000 or so. It is at 1,000,000, beyond 1,000,000, so it's growing very rapidly. It's growing exponentially, I guess is the word, since this is an exponential function, it's growing exponentially. The growth rate is more and more rapid as time goes on. All right, so I'm going to take a quick sketch of my exponential function. What we want to see in our sketch is that we're very slow growth followed by very rapid growth. That's a characteristic of an exponential function. Low growth followed by high growth if we're in an increasing exponential function. All right, so as they were saying, this is our exponential function given by p of n equals 2 to the n. And is this function discrete or continuous? Well, in this particular situation, since it's the number of generations and there can't be a person between you and your parents, like there's not a person in your generational line between you and your parents, it's going to be discrete. So even though we're drawing it continuously, it would really be only the whole number points. It would be only wherever these happen to be. I don't have scale here, but it would only be defined for whole numbers, which, my goodness, I have to fix this because I wasn't even thinking about continuous or discrete, unfortunately, when I did this. So this really should be in discrete notation, 0, 1, 2, up through 20. Apparently I forgot about chapter 1 while we're in chapter 3. I'm thinking domain, and I wrote a continuous domain, but it's not continuous. So that would have been continuous. We have to make sure it's discrete because the inputs have to be whole numbers. Just in this context, not in the general function, but just in this context. So forgive me for that mistake, please. helps us have a more full conversation. So hopefully it is still helpful, even though we had initially written the domain in continuous notation. We've got to fix it to write it in discrete notation. All right. Okay, so onward to our definitions of exponential functions. If you have an exponential function of the form y equals b to the x, where the base, the b value, is larger than 1, then you are going to have an increasing exponential function. So not only is it an exponential function, but it's an increasing exponential function. All right, I'll talk about that in the next page as well. I just figured I'd add that word in here. And then we'll talk some more about increasing exponential functions. Now, we're going to go back and look at that same function, but in its general form. So we're still looking at the 2 to the x function or 2 to the n function, but we're getting rid of context. Now we're looking at it generally. So the sketch of that, again, we've already looked at the sketch of this. They want me to zoom in to the window that has -10 to 10 on x and -2 to 10 on y. So we're zooming in on this a little bit here. And again, we see that very flat in the negative area, very flat up through, very steep. And the further across we pull this graph, the steeper it's going to get. Okay, so we can see our picture. And now, because the graph of this general function, the general function is continuous, no holes or breaks, what appears to be the domain of that function? Okay, so the general graph, again, we can see its shape. It goes all the way left. It goes all the way right. It takes forever to get right because it's growing tall so fast, but it does eventually get to the right. So the domain is going to be all real numbers or -infinity to infinity for the full function. We are not looking at it in terms of the context. Let me draw in a pair of axes right here. It's approximately where my x and y axes should have been. Then we need to talk about the range. So domain is x, it's left and right. Range is y, it's up and down. This function certainly goes up, and it goes up very rapidly. When it goes down, it does not go into the negatives. It actually comes down here and lays just on top of the x-axis. It doesn't actually hit the x-axis at all. It gets really close to it, does not hit it. So my range is going to be outputs y values that stay just above 0. I don't get to be 0, so we would use a parenthesis around the 0, or we could write this in inequality notation with y greater than 0. Not equal, it cannot equal 0. It's floating just above the x-axis right here. The y value is going to be slightly positive. It's not going to actually be 0, so there's no bracket. It's a parenthesis to not include the 0. All right. Determine the y-intercept of this graph. Okay, so if you're looking at your decimals, you should be able to see your point, but they ask us to determine it by substituting 0 into the equation and solving for y. So y equals 2 to the 0, putting 0 in for x, right? And I know from the last chapter that 2 to the 0 is equal to 1, so that tells us that we should have the ordered pair 0, 1. And if you check your graph, that is the ordered pair for the y-intercept at 0, 1. Is this function increasing or decreasing? So if you ride from left to right, it's certainly increasing. It's going up very rapidly. So it's increasing. All right, so here's what they talk about. That function again, y equals b to the x, is going to be an increasing function if the b value is greater than 1. So if b is greater than 1, then b is called the growth factor. So your graph is increasing for a positive b. And for each increase of 1, the growth factor increases by for each increase of 1, the output increases by a factor, a multiplicative factor of b. So it gets like, if the base was 2, it gets 2 times as large. That's what the factor means. Factor means a multiplicative factor. Multiplicative factor. All right, So we're going to have some practice identifying the growth factors, if any, for each of these functions. So the growth factors are our b values. I'm going to label them as b for our growth factor. The growth factor is the b stands for base of the exponential function. So the growth factor is 10. The growth factor of this one, the base of this exponential function, is 1.08. The growth factor of this next function is 4/3. It's the base of the exponential function. Now, they're throwing us a loop for this one right here because this base, unlike 10 and 1.08 and 4/3, this base 0.8 is not larger than 1. Even 4/3 is larger than 1. This is not larger than 1. So this base value is less than 1. So it is not a growth factor. It's a decay factor. We'll get to decay factors shortly. But for right now, it is not a growth factor. I'll write in parentheses that it's a decay factor. It's going to have decay because it's less than 1. So I don't have a growth factor here. So that's a kind of a trick question for this one when they want us to find the growth factor, is just to realize this function here is not growing. So these three are all growing. They're all increasing functions because the base value is larger than 1. This one's not. And again, this one is not going to have a growth factor because it's not even exponential. It's linear. So no growth factor. So it does not have a growth factor. It's got a slope. It's an increasing linear function, but it's not exponential, so it cannot have a growth factor. Okay, next, let's take a look at the next page. Return to this graph. Does this graph appear to have an x-intercept? Okay. So does it ever appear to cross the x-axis? And it should appear to not cross the x-axis. I'm going to drag on it for a second. Does the x value ever appear to get to 0? Right now it's 0.003, 0.002, 0.001, and then, oh, look, it says it's 0 when I'm dragging. It's not 0, though. It's not 0. It's just small enough that when it rounds it to 3 places, it rounds to 0. So let me take negative 13 for the input just for fun here. If we do p of negative 13, see how it's not 0? It's 0.00012. So it's just on the graph, they're going to round it to 3 places. So it's showing us a 0 there, but that's just rounded to 0. It's not 0 itself. So it's not actually touching the x-axis here. So I need to answer this here as no. It does not appear to have an x-intercept. It gets close, but it never touches the x-axis. Okay. And let's just go ahead and make our table so that we can fill in for -1, negative, getting the wrong keys today. -1 and -2 and -4. Okay. So our output values for -1, 0.5 for -2, 0.25 for -4, 0.0625 for -6, 0.0156 and so on, 0.0039 and so on, and 0.0, that one's in scientific notation, but I can put 3 zeros, then my 9 there. So 0.0000977. Or how about 98, just to get one more digit there. Okay, so they're getting quite small. And apparently they've noted this one for us for fun. I don't know why. We already could see it ourselves. As the values of the input variable decrease or become large or negative, what happens to the output values? So they get closer to 0, they get smaller, and closer to 0. They're not going to get to 0, they're just going to get really close. Okay, so we're going to use the trace feature. What happens as we get closer and closer to 0? Again, it's just getting smaller and smaller and smaller. I'm just going to repeat what we said here. They get smaller and they get closer to 0. I will also make the caveat that on Desmos, sometimes on the graph, it gives 0, but it's not actually 0. It's just rounded to 0. Okay. So when this happens, it's because the graph has a horizontal asymptote at y equals 0. The horizontal asymptote is a line that your graph approaches but never ever reaches. It's getting very, very close to it. So the horizontal asymptote is the line y equals 0, or the x-axis, and it's going to get closer and closer and closer to that line without ever actually reaching it. So we'll go from 0.5 to 0.25 to 0.06, 0.000001 as we get closer and closer and closer to the x-axis. All right. All exponential functions, regardless of their base, are going to have a horizontal asymptote. We'll talk some more about those as we look at some more examples here. Okay, so we want to make a table for a couple different inputs. Let me get rid of these two here. And a couple different functions. Let me first type my two functions. F of x equals 2 to the x again, I believe. And g of x equals 10 to the x. And we're going to make a table with -3, -2, up through 5. And we're going to want to input for both of our functions. All right. So for the 2 to the x, I've got the 0.125, then the 0.25, 0.5. 2 to the 0 is 1. Then I should have 2, 4, 8, 16, and 32. And for the 10 to the x, I have 0.001, 0.01, 0.1. 10 to the 0 is 1. Then I have 10, 100, 1,000, 10,000, and 100,000. So what we can tell from these is, first of all, that y-intercept that we were talking about when we plug 0 into the function, no matter what the base is, 2 to the 0 is 1, 10 to the 0 is 1, so these two functions have the same y-intercept. We can also see that what happens on the left side with these small inputs is similar. They're both getting very, very small, very, very close to the x-axis on this side. And what we can see on the other side is, again, when you have positive inputs, you're getting larger and larger. Now, the larger the base is, the larger you get as your output, but we are growing rapidly in both cases. The 10 grows a lot more fast because it has a lot higher of a base. We're multiplying by 10 each time instead of by 2. All right. Now, I'm keeping my decimals up here because that's what we want to do next is look at the two graphs and talk about what we can see on those graphs. So I'm going to just zoom fit. And hold on, it wants me to maybe not zoom fit because that made it this 10,000. That's so large. Let me go ahead and use the window that they've suggested. -5 to 5 on x and -2 to 9 on y. Okay, so I can see my two functions. This one that is lower is the 2 to the x function. This one that is higher is the 10 to the x function. And I don't see as many dots on this graph because these ones jumped so rapidly. I can see the 0, 1 point. I can't even see the 1, 10 point. Let me zoom out just a teeny tiny bit to see the first point. There it is. I have my first point up here at 1, and then I'm not even going to be able to see the rest because they grow so rapidly. Same shape. As you can see, the one that grows more rapidly is also shrinking more rapidly on this side. So it's lower and then it's higher. This one is going to be a little higher and then a little lower, but they have the same basic shape. All right, so we're going to just discuss the results, how they're similar and how they're different. Be sure to include domain and range, growth factor, intercepts, and horizontal asymptotes. That's a lot of things to write in here. Okay, so they have the same y-intercept at 0, 1. They have the same domain of -infinity to infinity. They have the same range. I'm going to just underline same because this is my box of same stuff. The same y-intercept, the same domain, the same range of 0 to infinity because they were not going below 0 as output and they weren't even getting to 0 as output. And then they have the same horizontal asymptote. At y equals 0. So that's a list of the things that they have in common or the same. And then for differences, we can say that their growth rates are different. They both have growth rates, but their differences is that 10 to the x grows faster than 2 to the x, or g of x grows faster than f of x, but I like to name them by 10 to the x so we can see the reason. Yeah, it's kind of the biggest difference. They both have growth factors. The growth factor is 10 in the first function, and the growth factor is 2 in the second function, which is the reason this grows faster. So that's really the biggest difference I know. Everything else I think is a similarity here. All right. Last question. Determine or examine the output pattern to determine which of these is linear and which of these is exponential. Okay, so linear, they're going to be an additive pattern. Remember, if you're doing linear and you wanted to calculate slope, you would do y2 minus y1 over x2 minus x1, chapter 1 stuff for linear. Linear is going to be additive because you subtract to find the difference. So you would add something to go from one to the other. So actually notice that right away right here. This is an additive difference of +4, right? This one is increasing by the same amount each time. This is an additive function. So if you subtracted these two, the rate would be 4 each time. So this set right here is linear because the change, the rate of change, is +4. Rate of change or slope is +4. Now, if linear is additive, there's a change that's either an add or subtract, then exponential is multiplicative. So you want to think about what the quotient of two y values might be, or what you would need to multiply by to go from one to the next. So if you, again, take 16 divided by 4, that gives you 4. That's why I'm saying that's how, if you weren't sure what you had to multiply by, you could divide two values. If you're not sure what you'd need to add, you could subtract your y values. But I can see that if I multiply by 4, multiply by 4, multiply by 4, that this is multiplicative. So this is exponential. And it means that it has a growth factor of b equals 4. I'm going to put m for this rate of change up here. Just comparing and contrasting. Additive change, slope or rate of change for linear, multiplicative change, growth factor is what we call it for exponential.